Okay, so last lecture we proved Cantor's theorem, and it stated that for any set X, the power set has strictly larger cardinality, meaning that there is an injection from that set to its power set, but there is no surjection or any bijection from that set to the power set. Now, I told you that there are three different, Cantor came up with essentially three different proofs. The first one was about closed intervals on real line. The second one was about 0-1 sequences. We constructed this table. I showed you the diagonal argument. And the third one was the one we did in class. And in order to describe the third one, what I did was, you may remember this, I listed, like, we basically list the elements of X in here. Maybe it's not countable, so this is not supposed to be really a list, but the point is, pretend for a second that X is countable. So these are the elements of X. And over here I listed subsets of X, and we looked at the subset of elements of X which did not belong to the set they're matched with on this table. You can turn this argument into a diagonalization argument using 0-1 sequences as follows. Construct a table like this. Over here you have the elements of X. Over here you have subsets of X listed somehow. Let's say this is the first subset. This is the second subset. I'm just making this up. This is the third subset, and so on. Now, if this guy belongs to this subset, put a 1 here. If this guy does not belong to this subset, put a 0 there, okay? Then, again, you can get a table of 0-1 sequences, and looking at this subset, simply, like, what this tells you is that look at the set of all X values which, well, what does this mean for X to be in the f of X? This means that, let's say that this guy is, how do you check that this guy is in this subset? Okay, no, I'm not making sense. I'm supposed to put, never mind. I'm supposed to put x0, x1, x2 here as well. Never mind. I'm taking that back. You can do it like this, but I don't want that. Sorry. List elements of X here, list elements of X here. Then, instead of, like, for any subset of X you want to list here, you're going to put zeros and ones here, okay? Let's say that you want to consider this subset. Then you're going to put a 1, 1 here and 0, 0, 0 for the rest. Let's say that you want to consider this subset. Then you're going to put a 1, a 0, and 1, and 0, and so on. You're going to do this. Now, the set of elements satisfying this is the set of elements of X which satisfy this are exactly those which have ones over here. So if this is 1, if this is 0, if this is 1, and if this is 1, this element satisfies this, this element satisfies this element satisfies this. Why? Because in order to check whether x2 is an f of x2, well, f of x2 is this subset. How do you check that x2 is inside this? If x2 is inside this, it means that for x2 I have put a 1 here, okay? So checking this is the same as checking whether there is a 1 or not. So the set of elements satisfying this is the set of X values for which there is a 0. Now, look at this subset. Looking at this subset simply means, remember the diagonal argument I showed you like 2 hours ago, it was over here with zeros and ones. We flipped the diagonal, right? Looking at this subset simply corresponds to flipping the diagonal. This subset, if I try to list it over here, it's going to correspond to 0, 1, 0, 1, 0, 0, and so on. It's going to correspond to the 0, 1 sequence, which is obtained by flipping this diagonal. So the diagonal argument we did in class with power set can be seen like a generalization of the diagonal argument I described with 0, 1 sequences. Of course, you're going to say that x need not be countable, and that's the case, but somehow use your imagination and pretend that you have uncountably many guys here and you have uncountably many zeros and ones in here, okay? This argument will still work, and indeed it works. We proved that. Anyway, that's that. And I told you a little bit about Cantor's first diagonal argument, and I want to sketch the proof of that. After that, we're going to start the actual material of this lecture. Now, for this theorem, I mean, this is for those, this is not in the scope of the course because of the following reasons. You don't know about, we don't learn about topology in this class, you don't know what a Cauchy sequence is, or we haven't constructed the real numbers yet. So for this question, pretend that you know what real numbers are, you know what a closed set is, and so on. Okay, so remember all the real analysis knowledge you have. So Cantor's original diagonal argument was the following I'm going to do on the board. So no function from natural numbers to real numbers is bijective. Okay, pretend that we constructed real numbers and you know what real numbers are, which we're going to do next week. Now, the idea is the following. Let's say that you have some function, any function, from natural numbers to real numbers. Construct a sequence of closed intervals I sub k recursively, well, not recursively, closed intervals, blah, blah, recursively as follows. So you choose I0 to be, let's say, this interval, closed interval, 0, 1. Okay? Choose I sub k plus 1 so that two conditions are satisfied. This is a subinterval of the previous interval, and f of k is not in I sub k plus 1. Okay? Now, maybe I should write proof sketch here because I don't want to prove that this can be done in detail. I'm just going to describe you why this can be done. Okay. You have a function. Let's say that these are the values of the function. F of 0, f of 1, f of 2. I'm just making this up. Like maybe the f4 is over here somewhere, f5 is over here. What I'm going to do is the following. I'm just going to choose one arbitrary interval at the beginning. Let's go with 0, 1. Okay, let's say that this is the interval 0, 1. Maybe 0, let's make sure that 0, 1 contains all this, okay? This is the interval 0, 1. This is my first interval, I0. In order to choose I1, okay, I want to satisfy the following conditions. This is a subinterval of I0 and it misses F0. So I need to choose some interval which misses F of 0. Okay, I can Okay, let's make this f6. Let me put f of 0 over here. Now I want to miss this guy. So let's take this interval. Now in the second stage, I want to find a subinterval of this I1 which misses f1. This already misses f1, so I can choose itself. At the next stage, I want to find a subinterval of this guy which misses f of 2. Now why can I do this all the time? Because you see, showing that this can be done basically amounts to constructing real numbers and proving that rational numbers are dense in real numbers. Why can I do this? Rational numbers are dense in real numbers. I'm talking like, if you don't know topology or what dense means, you can just ignore the following 5 minutes. Rational numbers are dense in real numbers. Moreover, rational numbers are countable. So what I'm going to do is the following. I'm just going to count rational numbers one by one, okay? At some point, I have to hit a rational. Let's say that I have constructed some interval. I did this construction up to stage k, okay? And let's say that f of k is over here. Sorry, yeah, f of k is over here. Now what I'm going to do is I'm just going to count rational numbers one by one. And I will stop at the first rational number, which is different than this guy and which is in this interval. Let's say that it's this rational number. Now I'm going to look at closed intervals around this rational number with rational radius. With radius 1 over, indeed with radii 1 over 1, 1 over 2, 1 over 3, and so on. I'm going to look at closed intervals around this point with radius 1 over 1, 1 over 2, 1 over 3, and so on. Now, at kth stage, well, okay, up to kth stage, I'm only dealing with k many points. And I'm looking at radii 1 over 1, 1 over 2, 1 over 3, dot, dot, dot. That set is infinite. I have finitely many points. So for some radius, this interval will have to miss all these finitely points, f0, f1, f2, dot, dot, dot. So I can find a sufficiently small closed interval which misses all the points up to fk. And I'm going to choose that closed interval to be my next interval, okay? So just using the fact that rationals are countable, you can just explicitly write a formula for this. You can say that ik plus 1 is this closed interval centered at this rational number with the blah blah radius. This can be explicitly chosen. Now, by Cantor's intersection theorem, the intersection of these guys is non-empty. I'll explain why this is the case. Let x be in the intersection of these guys. Then x is not in the range of f. Now pretend for a second that the intersection of all these closed intervals is non-empty. Okay? Let's say that there is some x which belongs to all these closed intervals. I claim that this is not in the range. Why? Because the kth closed interval avoids the kth number here. Which means that, and this x is in all of these ik's. Which means that, sure, go ahead. Which means that this x has to, it cannot be of the form f of k, because f of k is missed by ik plus 1 and x is inside this. So this x is simply not in the range of f, okay? Now this is the first diagonal argument Cantor came up with. It uses some topological fact, namely that if you have closed intervals on real line which are nested, which are like which are sitting inside each other, then their intersection cannot be empty. This is actually, it follows from a more general topological fact. Like if you have a Hausdorff space, if you have nested compact sets which are living in each other, if they go like this, their intersection cannot be empty, okay? So for the specific case, like you can, I think, prove this using completeness of real numbers, like that real numbers form a complete metric space and so on. That's the topological part. So given that this is an empty, you can find some number outside the range of this. Now, why is this called diagonalization? Why am I still calling this a diagonalization argument? Because the essence of diagonalization arguments are the following. You list various stuff. At the end, you want to produce an object which is different than all the stuff you listed. And what you do is, you do a construction where at the kth stage, you make sure that the object you're going to produce is different than the kth object you listed. If you look at this construction, what I'm doing is, I'm constructing these intervals so that whatever I'm going to get at the end is different than the thing I want to avoid at the kth stage. Okay? Basically, all diagonalization arguments have this spread inside them. You have some conditions and you have some objects. You want whatever you're going to produce to be different than these objects. So you make sure stage by stage that whatever you're going to produce is different than what you listed. Okay? So this is a diagonal argument as well, even though there is no diagonal here in this case. There's no diagonal that you can see. Anyway, questions about this? Now, this is not a full proof, and I said sketch here because you need to prove that this can be done. You can choose such ik plus 1, and you need to prove Cantor's intersection theorem and so on. I just want to show you that Cantor's original proof was nothing like what we proved. That's what he did in probably 1891 or something, and this dates back to 1870s, 74, 75, something like that. Anyway, the point is, uncountable sets exist. Okay? Now, I don't want to talk about uncountable sets for the rest of this lecture because the rest of the course is going to be about uncountable sets. Okay? So, for the rest of the lecture, I want to focus on a very nice theorem called Cantor-Schroeder-Bernstein theorem, okay? And it says the following. So it took 3 guys to actually prove this. I don't know whether they collaborated or not. I'm not sure. I know that Cantor did not collaborate with these guys because this is sometimes called Schroeder-Bernstein theorem, sometimes called Cantor-Schroeder-Bernstein theorem. Anyway, it says the following. Let A and B be sets if, bless you, there's an injection from A to B and an injection from B to A, then there's a bijection between A and B. Remember, we showed this by the notation, by this notation. And we showed the existence of such an injection by this notation. And we showed the existence of a bijection by this notation. Now you see that the notation we used actually makes sense. If cardinality of A is less than or equal to cardinality of B, if cardinality of B is less than or equal to cardinality of A, then their cardinalities are actually the same. Now, I want to prove this. The proof of this is, it's really cool. Well, okay, first of all, there are various proofs of this. Just like any fundamental theorem in mathematics, people have come up with many different proofs. I don't know to whom the proof I'm going to do belongs. Maybe it's Schroeder's proof, Bernstein's, I don't know. I didn't check that, but I really like this proof. I'm going to draw a big picture, a giant picture, and you'll when you look at the picture, you'll realize that this is a really cool idea. Everything works out, and then you'll realize that this is so obvious. You see, this is one of those theorems which is not obvious until you see a proof. I mean, if I ask you to prove this, you're going to have some trouble. This is not easy to prove. This is non-trivial. However, when you see the proof, you'll be like, oh, of course this is supposed to happen. Well, it's supposed to happen if you draw the correct picture. Now, let F be an injection from A to B and G be an injection from B to A. Let this and this be injections. Okay? So I'm assuming that there's an injection from A to B and there's an injection from B to A. I want to show that there's a bijection between these two. This is too big. This is still too big. This is A, and this is B. Now, there's an injection in this direction, which I called F. There's an injection in this direction, which I called G. Recursively construct the following sets. I'm going to have A0, and it's going to be equal to A. I'm going to have B0, and it's going to be B. Now, what I'm going to do is I'm going to apply F to A0. Okay? So this is F of A0. And I'm going to apply, do I have another color here? I want more colors. Okay, apparently I don't have any color. So I want to apply G to B0. Okay? And G goes from here to here. Now, I'm going to define A1 to be G of B1, but I didn't tell you what B1 is. B1 is F of A0, okay? Now, this is supposed to be B0 as well. Yes, this is. Yes. In general, let me write down the general formula. This is supposed to be Bn. This is supposed to be Bn plus 1 is supposed to be F of An. Okay. So, what I'm doing is the following. This is, I apply F to A0. This becomes B1, okay? This was B0, this was B1. And this was A0, and this was A1. Now, I'm going to apply F to this guy again. Okay? maybe I should write that down. You see, B2 is, what is B2? B2 is f of A1. So I'm just going to apply f to this, and this is going to be my B2. And I'm going to apply G to this guy. And I'm going to get A2, okay? So this is going to be my A2. So this maps to that. And yeah, everything is good. Now I'm going to keep doing that for every n. So apply f to this, apply g to that. Okay, and this is A3, this is B3. I'm not going to go for more because I don't have enough space. Now, is this understood, what I'm doing? Okay, apply F, apply G. You have these smaller guys. Apply F, apply G. You have these smaller guys. You keep doing that. Maybe this is empty. Maybe when you apply F, you get all of G. It is possible, so this may be empty. I don't really care about that at the moment. Now, it is easily seen that the following happens. These ANs and BNs form decreasing sequences of sets. When I say decreasing sequence, I mean this. The next one is a subset of the previous one. Okay? Why is this true? Why is this easily seen? You can prove this by induction, okay? Like, assume that this holds up to some n, then it's going to hold for the next n. And it's actually clear on the picture, right? Okay. Now, let D be the intersection of all these ANs. Okay, I go here, I come back, I go there, I come back, I go there, I come back, blah, blah, blah. Let's say that I take the intersection of all these guys. This may be empty. It may not be empty. I don't know. Let's call that intersection D. Consider the following function. Now, I'm going to define a function. This will be defined from A minus D to B. And it's defined as follows. H of x is defined to be, let's see, f of a if a belongs to am plus 1 minus an, sorry, am minus am plus 1 for even n, for some even n, okay? And I'm going to define this to be G inverse of A if A belongs to, again, this difference for some odd n and n, okay? Now, what am I doing? Let's try to understand how this function behaves. First of all, why is the domain of this function a minus d? Well, okay, I'm defining it like this, but never mind. Let me erase this for a second. We're going to figure out that its domain is a minus t. So let me not specify the domain and range at the moment. I want to define a function which behaves like this. For even n values, the stuff in an minus an plus 1 is mapped to be via f, and the stuff in an minus an plus 1 for odd n is mapped to be by G inverse. So what I'm doing is the following. A0 minus A1. 0 is even. I'm mapping all these guys via f here. So green region is mapped to green region. Okay? A0 minus A1 is mapped to here by f. For odd n, I use G inverse. Let's choose an odd number n. 1. 1 is odd. So stuff in A1 minus A2 is mapped over there via G inverse. What's going to happen to this guy when you apply G inverse? You're going to get that. Okay? You're going to get this part. Now, what I'm doing is that complicated definition I wrote over there exactly does the following. It takes this, okay, I'm going to call this a ring because it looks like a ring. It takes this green ring and it maps it to this green ring. It takes this white ring and it maps to this white ring. So it pushes this down, it pulls this like this. Now, this green region is going to be mapped to, let me put 2 circles there. This green region will be mapped to this green region. And let's ignore this D. This white region will be mapped to this white region. So green goes to green, white goes to white. Green goes to green, green goes to green, white goes to white. You see what's happening? Now, what's the domain of this function? It is the union of an minus an plus 1s, right? What is this? This is all of A except the intersection. Okay, so the domain of this function is all of A minus the intersection. Okay? What's the range of this guy? Just by looking at this picture, you should be able to actually tell me. It's going to be B minus intersection of these guys. Okay? Now, consider the following function, blah, blah. I'm going to leave this as an exercise. Check that this H is a bijection. Okay? Check that this is a bijection, this H. Now, I'm almost done. I found a bijection from a huge portion of A to a huge portion of B. And when I say huge, I'm just saying it by looking at this picture. Maybe there are many, many elements in here. I don't know. But for most part of A, I was able to map this part to this region except this white region, okay, by a bijection. Now, if I can find the bijection between this intersection and this intersection of ANs and intersection of BNs, then I would be done. Because I will take the union of these two bijections, and that's going to be a bijection between A and B. That's exact. And we already have a bijection from this little guy, from the intersection of ANs to intersection of BNs. It is F, okay? Now, since F is injective, we have the following. Let's look at the image of D under F. Well, D is the intersection of ANs. Okay, I'm going to call intersection of BNs something E. No, I don't need that. I don't need more symbols on the board. Anyway, image of F under D is, well, D is the intersection of ANs, so image of this intersection. Now, because F is injective, you can take this intersection out, okay? Well, what is F of A sub n? What's the image of AN under F? It is by definition Bn plus 1. Okay? But this is the same as intersection of BNs because I'm taking the intersection. I mean, these are nested sets. Bn plus 1 is a subset of Bn, so this is going to hold. Now, this H is a bijection from A minus the intersection of ANs, A minus D, to B minus intersection of BNs. Any injective function is a bijection from its domain to its range. Its range is the intersection of BNs. H is a bijection from here to here. F is a bijection from here to here. Thus, their union is a function. This is a set of ordered pairs. This is a set of ordered pairs. Their union is a set of ordered pairs. And the domains of these functions are disjoint. So when I take their union, it's going to be a function already. So this is their union is going to be a function from, let's see, what's the domain of their union? This union, this gives me A. And what's going to be the range? What's going to be the codomain? This union, this. So it's going to be B. Well, this is a bijection, this is a bijection, this will be a bijection. Okay? So, this is the Cantor-Schroeder-Bernstein theorem. It shows that if you have an injection from some set to some other set, and if you have an injection in the other direction, then there's a bijection. And not only it shows the existence of such a bijection, it kind of tells you what to do if you already know, if you know the injections. Take this set, take this set. Let's say that you have an injection in this direction. You know the injection in this direction. You have the injection in this direction. Then you do this thing. You apply F. You apply G. You apply F. You apply G. You keep doing this. Take the intersection of these guys. These are my ANs, these are my BNs. Take the intersections. Now map this intersection to this intersection via F. For the remaining rings, what you do is you take this ring, you map it to this guy. You take this ring, you map it to this guy. And you go like this. Like you take two rings, you map one with F, the other with G inverse. And you keep doing that. At the end, you will exhaust all the elements, okay? What I'm trying to get at is, if I tell you the injections explicitly, this proof shows you how to explicitly construct a bijection, okay? It's going to be a complicated bijection when you try to write it down. You see, like, we're defining it piecewisely for each of these guys. You have to calculate these and so on. Nevertheless, it's explicit. It tells you what to do, okay? It's not just an existence proof. Now, questions about this? This is important, okay? We're going to use this to show many things are equinumerous, okay? Like in future, when I need to show that two things are equinumerous, I'm not going to try to find a bijection between them. I'm just going to show that in both directions there are injections. For example, remember, okay, let me create a little box to myself. Last lecture, we proved that n cross n is countable, right? Countable infinite. This is equinumerous with n. I gave you an explicit bijection. We didn't have to do that. We could have done the following. Take mn, map it to 2 to the m, 3 to the n. This is an injection because of the fundamental theorem of arithmetic. Okay? Positive naturals can be uniquely expressed as product of primes and so on, blah, blah. This is an injection. In the other direction, I have another injection. M goes to M0, this is an injection. So there's a bijection between n and n cross n. Okay? Using the proof, you can construct one using these two injections. It's going to be a complicated one compared to what we found, but it shows you there exists a bijection. Okay. Questions about this? No? Did everybody understand the proof? Forget about the stuff I wrote over here. Did everybody understand the picture? By applying f and g recursively like this, apply f, apply g now to these little sets, apply f, apply g, you create these what I called rings. Now, take this guy, map it by f, take the next, pull the next one by g inverse. Push this one by f, pull the next y by g inverse. And then you're basically like intertwining these rings, like you're gonna putting them like this. You take these two, you put them like this. You take these two, you put them like this. You keep doing that, and you can do this for all elements except the ones in the intersection. The ones in the intersection, you simply push them by f, okay? Questions? No? Okay. Now, I'm going to stop here. Let me tell you what we're going to do next lecture. So, in my notes, we have finished everything up to section 6, okay? Which is the construction of various number systems. So, in next lectures, maybe for the next hour or maybe for the next 2 hours, I'm going to construct integers from natural numbers, and I'm going to construct rational numbers from integers, and those are going to be easy constructions. And after that, I'm going to construct real numbers. That's also going to be an easy construction, but we're going to spend some time on it. We're going to prove that the real numbers have the completeness property. You know the supremum property, right? Any subset of real numbers which is bound above has the least upper bound. We're going to prove that because that's basically, that might be one of the facts that's used most frequently in all of your courses. I mean, your calculus courses all depend on that, okay? So that's an important property. We're going to prove that after we construct real numbers. There are various approaches to construction of real numbers. One of which you might have seen in your real analysis course. You first construct rational numbers, you put a metric on it, and then you construct real numbers as the Cauchy completion of the metric space of rational numbers. It's a topological construction. You construct Cauchy sequences, you just quotient out by some constellation, blah, blah, blah. I can do that, but that's already done in 349. So I'm not going to do that. Instead, I'm going to show you the Dedekind construction, the construction of real numbers with what's called Dedekind cuts. A real number simply will be a subset of rational numbers, okay? A subset satisfying certain properties. Then we're going to collect all those subsets of rational numbers satisfying whatever property I'm talking about into a single set, and we're going to call those real numbers. We're going to put an ordering code on those subsets on real numbers. Then we're going to prove some properties of real numbers, like the completeness property. With some effort, you can show that together with the operations I'm going to define, the real numbers form a complete order field. I don't want to do that. It's in the textbook. I mean, we can change the course of this class towards that direction, but I don't want to do that. I want this class to be about ordinal numbers and cardinal numbers, basically, which is, according to our syllabus, it's the second half of the course. So I'm not going to spend much time on like proving that the rational numbers as we're going to define them form a field and so on. You can read those in your textbook. I'm just going to do the basic constructions. I'm going to prove that the real numbers have the supreme property, and then we're going to start talking about ordinal numbers, okay? So, I'll see you next week.